So happy Friday, everybody. For anybody that wasn't here last time, I have extra copies of the lectures, notes. So two hours worth of lectures are stapled together, last week's and this week's. So if you were here last time, then you don't need a copy. That's the attendance register. Anybody have any questions before we jump in to today's exciting topic? So everybody has the first assignment under control. Good. Then Tom's going to have a very easy job, just giving everybody 100 points because everybody knows what they're doing. It's going to be a delight to read the amazing design reports.
Can't wait.
So today's topic on protocols, this is one of my favorite lectures. I really like the material here. And we talk about things that are very simple and very important at the same time. So none of the stuff that I present today is very complicated. It's simple, but that doesn't mean it's not important. And we talk about some things that software developers generally don't ever think about in their day-to-day lives that are simple and extremely important, that have massive consequences. So it's a fun topic, and I really enjoy it. And this is one of my favorite slides. Not only one of my favorite lectures, but this is one of my favorite slides. So there are the designs, a design or a schematic of two web server programs, right? One of them is a Linux web server, and one of them is a Windows web server. Right, and this is a map of system calls, so to speak, client-server calls in the context of this module, right? So every time a single web page is served by one of these web servers, this is the series of system calls that takes place. That's every time, right? Every time a web server feeds a page to the client, right? So this is a security, this falls also under the security topic. So this is one thing that hackers look at for when they're looking for vulnerabilities in a web server, right? So hackers investigate each memory access to see if it's vulnerable to a buffer overflow attack, right? So imagine, this is going to happen to a lot of you, by the way, if you go into the software development business. This is actually going to be, for the majority of you, your first job or your first assignment. After you start, they're going to say, okay, we have a piece of software with some bugs. Can you fix them, please? Like that's going to be your first assignment for most of you that enter the software development business. So imagine this is the software you're given. Or you have a choice. You can say, we have some bugs in the Linux web server, or the top, or one of these. You can choose. Like, you can choose between this program and this program to fix the bugs that we have. Which one would you choose? The first one. That's right. So does everybody see a difference here between the design of this web server software, and this web server software? Does everybody see that there's a difference there? These are all, you could also think of those as collaboration diagrams. And we talk about collaboration diagrams in this module. And if you use Doxygen for your software documentation in this module, you'll discover that Doxygen can create these call graphs automatically. Right? You just feed it the software and it automatically generates the. So from a security point of view, the more system calls, the greater the potential for vulnerability and the more effort that's needed to create secure applications. Anybody want to guess which one is Linux and which one is Windows? The top one is Linux and the bottom one is Windows. So this is a one slide summary of why most of the web servers in the universe are running Linux rather than Windows. Right? If your job is to fix the bugs in this software, guess what? It's not going to work. You're just going you might get lucky and fix some bugs, but you'll just end up creating more bugs. And it's because there's two things going on. There's no design process reflected here. This is what happens to software when there's no design process, when it's not designed. There's no plan. Remember we talked about the very first lecture, the software crisis. And the software crisis is the result of no planning. That's what we're talking about, software design, which is the plan of how to build your software. So that's what happens. And does anybody remember, we also mentioned that most projects fail, the majority of projects fail. That's right, so the majority of projects end up like this. Yep. And if you're interested in seeing more information, like reading the details of the article, I've put the details of the article here if you want to read up on it. So it's one of my favorite slides in the module. So today we're going to talk about protocols, and this is the transition from design to implementation. So we spent a lot of time talking about design. Does anybody remember why we talked about designs? We spent the most time talking about design up until now. Does anybody remember why? The attendance register is hanging around here somewhere. I'm going to be really proactive today. So nobody remembers why we were talking about software design, besides the fact that this is a software engineering principles module.
You've got to have good design to implement.
Say it again?
You've got to have good design to implement.
That's right, that's a good answer. That will score you points. Another reason is, if you remember back at the first lecture, software design is the least understood aspect of software engineering. It's the part that nobody understands, right? This is a product of the richest company in the world, right? They have software developers from MIT, Harvard, everywhere. You know, the best software, the access to the best software developers in the world, right? And they're producing this sort of stuff. The software design is the least understood aspect of software engineering, right? That's one of the reasons I like it, but that's one of the reasons we talk about it a lot in this module. So we're talking about the transition from design to implementation, and that's going to be in the form of protocols. Right? So protocols are a set of signatures to which a class responds. It's the final step of the design, or the transition from the design to the implementation. Signatures is another way of saying method name, input parameters to the method, and return parameters of a method. So you're specifying that first line of a method. Right, the method name, input parameters, and return parameters. So you specify all your protocols as your next stage, and then you implement the methods, right? So we construct protocols for each class specific signatures from methods, right? Good decisions require careful attention to refining responsibilities and naming messages. So we're starting to dig into simple material that people don't think about very much, right? We write a design specification for each class and subsystem, and we write a design specification for each collaboration. So the goal is to produce a precise and complete design that it could theoretically be handed to somebody else and they could run away and implement it. Right? Specifying protocols or method signatures often exposes funny and incomplete areas of the design. So this is where we start the implementation, and this is how we start the implementation. So far, we have a set of classes that are defined in terms of their responsibilities and collaborations. And then the implementation starts by defining these protocols, right? We need roughly one protocol for each collaboration, more or less. Could be two, could be three, but generally it's one. And there might be some protocols for private responsibilities that can happen. And we also want to avoid over-specifying the implementation detail, right? So we're not actually talking about the method body, the what comes after the method signature today. That's for later, right? We're still talking about what happens, not how it happens. We're specifying, remember that? A long time ago, I kept saying the design is about what happens and where it happens, but not how it happens. Hopefully somebody remembers that. And so that let's dig into this. So let's talk about method names. So a lot of people don't even think carefully about choosing their method names. So we're going to talk a little bit about that. So method names need to preserve encapsulation and general class utility while implementation details. So does anybody remember the golden rule for choosing method names? This is something that I hope everybody remembers for the rest of their life, actually. Correct. So methods, that's step one. Method names are verbs. So careful, thank you. What's your name, by the way?
Elliot.
Elliot. Thank you, Elliot. Careful selection of method names is critical for maintaining and reducing the design complexity. We also talked about overloading, right, which was also called polymorphism. Proper overloading can be an important vehicle, but be careful. Confusing one name used for two conceptually different things, that's not allowed, so to speak. We don't want to do that. A good example of proper overloading is the Java toString, right? That always means an object can print itself, or can print out a string representation of itself to the console, right? So we don't want to. I guess I'm not going to dwell on bad examples of overloading because that just might make things more confusing. So the choice of method names is as important as the choice of class names. Everybody remembers the golden rules for class names.
It should be nouns.
Nouns, that's right.
And singular.
Correct. Nouns, singular nouns by default. That's correct. Is it Demetrius? No. What's
George.
Georges, okay. I wasn't even close. Thank you, Georges. So each method name should imply a unique intent. Use the same name everywhere as a conceptual operation. Right? So be consistent. And associate a single conceptual operation with each method name. Remember, responsibilities map to methods. So everybody, it was a long time ago that we talked about that, but that's still true, even though we talked about it back in November. So let's look at some examples. Remember our amazing drawing editor program. Right, we have a class called Drawing and a class called Drawing Element, and they both have a display message, right? Even though their implementations are different. It's conceptually the same. Each object in a drawing program knows how to display itself or render itself, right? We could consider a hierarchical relationship, right, by introducing an abstract class like drawable object, right? And they could inherit the display responsibility. That's a possibility. So let's look at some actual examples of protocols. Does anybody know where you can see tens of thousands of examples of protocols already? If you're ever looking for examples and need to feel inspired. No ideas? I'm feeling very proactive today. Ed DeLacy? Where's Ed? Ed, any ideas where we could find tens of thousands of examples of these protocols in our daily lives? In our daily computer science lives? Nice! Yes, it's Friday morning, but you are awake. Exactly. The Java API, that is a set of protocols. Right? So if you're ever wondering, oh, what does a protocol look like? We're going to talk about it today, obviously. But the Java API is a set of protocols, and there are lots of them, right? Lots. I don't know how many. That would be a good coursework, like go find out how many there are. So a protocol for each collaboration must cover the full generality of each responsibility in the collaboration. Say that 10 times fast. So an array is responsible for knowing its size. So this is what a protocol for an array might look like, the array class. It's very specific. A more general responsibility might need several different variants of a protocol, right? Or several different variants of a signature, and you see this in Java a lot. So, for example, enumerating over a set of elements in an array. So, we could have a find first method, or a find last method, or a find all, and so on. So this is a general set of protocols for searching arrays. And they're all variants on a theme. They're all variants on the search theme. And they all return, these are all the return values, and these are all the input parameters. Here's something that a lot of people never think about, or they try not to think about it. And that's choosing default values, right? Classes are more easily used and more reusable if the protocols are designed to reflect their different uses. It's good to speculate on future use as well as the immediate uses, and it helps us to abstract and generalize. So we always start by defining the most general, most generic message or protocol. And then we have different variants that allow clients to specify all the different input parameters. But we provide default values for the input parameters wherever we can. And usually you can always define some default values or default parameters. This is something that is extremely important. Provide default values for parameters as appropriate. Default values have absolutely huge consequences. Does anybody know why default values have such huge consequences? That's not an obvious question and answer. That's not something I would expect people to know necessarily. Default values have enormous consequences because generally people don't change default values, generally speaking. And that's why they have absolutely enormous consequences. So just a simple example is printing, right? The default value for the printers here is print on one side of a sheet of paper, even though all the printers are two-sided. Somebody made the decision that this is going to be the default value for printing. Print on one side of the paper. This has ridiculously enormous consequences, right? Because so many people they're in a hurry, they don't change that default value to two-sided, and we end up at least doubling the amount of paper we use, right? Just because of this one decision of making the default value single page rather than double-sided, right? So default values have really enormous consequences. So that's why in this module we think carefully about our default values, and we know how important they are because they have tremendous consequences. So we analyze likely uses of each method, and we determine a set of signatures that require only subsets of parameters in order to make the signature match most naturally to each likely use. And defaults are used on unspecified parameters. So if we were going to write, for example, a display method in our drawing editor example, this is what it might look like. So a complete specification of the display method for the drawing editor might have some of these parameters, right? Which device to display, right? To draw to, right? We have multiple screens or multiple devices. A background color, right? That's another something we also have to choose default for. A default background color. I worked at a company that had the strangest default background color in their software, and nobody ever changed it, and it looked really horrendous. It's very, very common, very common. A clipping region of the display coordinate system, for example, only elements inside the clipping region are displayed. And a drawing rule indicating how images are to be overlaid, right? And we need default values for all of these as well. We have to think carefully about the default values. So another thing we're going to think about very carefully is the order in which we put the input parameters. So this is, again, very, very important, but something that nobody thinks about. So the order of the input parameters is based on the probability that the client will want to specify the parameters, so their popularity. So the most frequently used parameter is put first in the list of parameters, and the least frequently used is last. Now you might not know what the most frequently used input parameters are. But you can make an educated guess. Right? In the display example, probably, I actually, maybe the device to receive the display might be the most popular, or the background color. I guess the background color might be the most popular specification, but actually there's one that's going to stand out as clearly the most popular sort of set of input parameters. Imagine this is the display method we're trying to specify. Can anybody imagine which version of the display method, if we have multiple display methods with different input parameters, which one will be used the most frequently? This is a very tricky question, by the way. I wouldn't necessarily expect people to. So imagine we have to write a display method, and we have to cover all these different possibilities. Like we'll have a display method that takes the device as an input parameter. We'll have another one that takes the background as an input parameter. We'll have another one that specifies a clipping region, a drawing rule, and all the combinations, different combinations of those. Anybody know which one's going to be the most popular? So the most popular version of the method by far, like 99.99% of the time, will be the display method with no input parameters. In other words, the display method that uses all the default values. This will be the most popular called version of the method by far. And this is again why default values are so important, because they usually don't get changed. Right? So we want to specify a default display, which is the currently active window, a default background color, like white, for example. And I've seen some strange choices on this. You've probably been in presentations as well with strange background colors like dark blue with yellow font and red font and stuff like that. The default clipping region is the entire display area, and the default drawing rule is over. That means whenever you draw something, it draws over everything that was drawn before it. That's the rule that we're talking about. So it's like the most recent is on top, so to speak. The probability of somebody changing the display in a region are probably, we could argue that they're the most likely to be specified. Personally, I think they're never going to be specified. In drawing rule, it's very unlikely that somebody's going to change the drawing rule, right, and say, okay, all the most recently drawn items should be at the back or underneath. That's very unlikely, right? So in your group, you would have a discussion about which ones you think are the most likely. And this is a set of signatures that we can derive based on that discussion, right? We have a display method with no input parameters, and a display method that takes the device as input, and so on. Right? Guess which one is never going to be used? Nobody's ever going to call this method. Nobody. Right? Has anybody noticed the more input parameters a method requires, the less likely you are to use it? Has anybody noticed that yet? It's not fun to try to find 5 or 6 method parameters to give to a method just to use it. Right? So the more input parameters it takes, the less reusable it is, and the less likely it is to be used. So in all cases, the methods with no input parameters are the most likely to be used, right, as a general rule. We could think about these other variants of the display method, right? But when we do our protocols, we want to think about all these variations. And if you look at the Java API, they do the same thing, right? You have a method, they have a version with no input parameters, and then they have lots of different variations considering different input parameters. And you'll notice that they're usually ranked by popularity as well. So the second one will have one input parameter, and that's the most popular variant, and so on. So a little bit more on precedence, or the order, or the ranking of the input parameters. Trying to identify the precedence of parameters may actually lead to new design decisions, right? And this is very common, by the way. So if we don't agree on the precedence, we might want to have an alternative set of responsibilities and protocols that sort of carry out the same functionality. So this is the approach that I always use, right? Instead of specifying input parameters to constructors or those other kinds of methods, we have accessor methods that set and get specific parameters and specific attributes. Like we have a method called set current display device, and set background color, and set drawing rule, and set clipping region, and corresponding get methods for all those parameters. Right? And then you have to decide, okay, well, where is that data stored, right? And that's going to be something you have to decide in your design, during your design process, right? In this case, drawable object is a good place to put these responsibilities, right? And these responsibilities would correspond to class variables, right? That are stored in the drawable object class and accessed with accessor methods. Right? That's the default. That's the way I personally design all of my software. We might also introduce a new class called logical display to handle these tasks, and the drawing methods stay simple and focused. That might be a little bit more complex than we need. So now we know how to specify protocols, right? This is sort of a summary of the design document. Right, this might not correspond. This doesn't have an exact correspondence to assignment, your design document assignment. But it's sort of a summary of the design process, or the design documentation, let's say. So the hierarchy and collaboration graphs are updated and revised to reflect the final design decisions. So after you've discussed your protocols, you've specified your protocols, right? Hierarchy graphs each are on their own page. For example, a single page system overview is also highly desirable, including all the hierarchy roots or the parent objects and all the subsystems. And if it's possible, the first level children. I think in the assignment in this module, that would be possible to include that on one page. And collaboration graphs, I'm not sure if collaboration graphs are part of the first assignment or not. Do we have those or not? I can't remember. I think we have hierarchy graphs and subsystem graphs, but not collaboration graphs. So congratulations. You'll learn that Doxygen also creates collaboration graphs automatically. Each class must be fully specified, right? In the textbook, they talk about getting rid of the cards, the class CRC cards, and then actually putting the information in a document, right? So each class could have its own page, or each class could have occupy its own half of a page. And what do we specify for each class? The class name, whether or not it's abstract or concrete, right? The parent class, the child classes, any references to the hierarchy and collaboration graph, locations, which page those drawings are on. There's a class description, right? What is the class for? What is it intended to be used for? We list each collaboration on the class, and we list each new collaboration that we've inherited from our parents, for example, right? And for each responsibility, we have the method protocols that carry out that responsibility, that implement that responsibility. We can even put in private responsibilities if we want to. I would say this is not imperative. This is not. I wouldn't worry about that at this point, actually. And we might have an area that just has notes for anything else that we think is important, right? Any implementation notes or guidelines, error responses, performance requirements, and so on. One thing we didn't mention yet is return values. Return values for protocols. Does anybody have a good suggestion for a default return value on a method or protocol?
String.
A string? Why should the string be a default? What would the string contain?
Bits that can be converted into any other data type. Can be converted into any other data type.
Mm-hmm. And somebody also shouted the Boolean. Who shouted that? Was it you, Georges?
Mm-hmm.
No. That's correct. If you look at the Java API, the default return value is always Boolean. If you look at a beginner level software developer that doesn't want to think too much about return values, the default is void, unused. So by default, we want to return a Boolean value that returns true if the method is successful and false if it's not successful, right? Because a method might not succeed or it could succeed, right? And we want to test if methods are successful or not before we can continue on. And we want to be able to handle errors if methods don't succeed. Okay, subsystems are similar to classes, the subsystem documentation. So the subsystem is at the top of the page. We have all the classes in a subsystem listed. We have all the references to hierarchy and collaboration diagram pages. We have a description of the subsystem, its purpose and intended use, right? And we have a list of the collaborations supported by the subsystem. And for each collaboration supported by the subsystem, we identify a class or subsystem to which the collaboration is delegated. So a subsystem is documented very similarly to a class. Right? So after the entire design documentation process, we have one or more hierarchy graphs showing inheritance and overall class structure. We have one or more collaboration graphs, although the collaboration graphs are not required in this first assignment. A set of formal collaboration specifications defining servers and clients, and then class and subsystem specifications with the purposes described, the relationship to other classes and subsystems, collaborations and responsibilities, and implementation notes. So when you are doing that first design document, don't forget the in-class exercises that we did. The in-class exercise 1 and in-class exercise 2. It drives me bonkers. It's not going to drive me bonkers this time because Tom is going to assess. But it drives me bonkers to see that when those exercises are not incorporated into your first assignment, right?
Sorry, where are the exercises? Which level?
So where are the exercises? The exercises, if you go to my teaching page, and then you find this module. So this module, Software Engineering Principles. And then you can add the 2 letters E1, for example, onto the URL, and you'll get exercise 1. And you can change that to a 2 to get exercise 2, right, if you want to get those exercises. But don't forget those. Actually, don't forget those for the rest of your life. If you decide to undertake software engineering, and you don't forget those for the rest of your life. And this is, by the way, these exercises can be used to identify if you're working on a failing project or not, right? If you start your first job and the current software design does not follow these guidelines, you're working on a failing project. I can say that with 90+% certainty. So don't forget that for the rest of your life. Any other questions?
So does anyone want me to put those links to exercises on the Blackboard page? Would that be useful for someone?
Yes, please.
Yeah, I can do that.
That would be great. Thank you, Tom. Any other questions about the lecture or the coursework or anything like that? Good. Happy Friday.
Hey guys, today is Bob's last time with us. So before enjoying your time with me, nice step of thing.
Tom is going to take over the hard stuff now.